Welcome to Bodhi Bytes.
This is where we take a stack of sources, articles, research papers, notes, and really, dig in.
Yeah, get right into the thick of it.
Our goal, to pull out the most important bits, the key insights, maybe some surprising facts, basically help you get up to speed quickly and hopefully spark some aha moments.
Absolutely. And today, we're diving into a really fascinating corner of physics, quantum materials.
Yes, where things get seriously weird.
They really do, especially at, super low temperatures or under massive pressure. Electrons and spins they don't follow the usual rules. They challenge our standard model.
Right, we're talking about these really exotic states of matter. And the sources you've brought today, they focus on some pretty specific phenomena within that world.
Exactly. We're looking at behaviors where electrons just act differently than expected. Non-Fermi-liquid behavior, that's a big one.
Okay.
And points where materials are sort of balanced on a knife edge at absolute zero. Quantum critical points.
Right, and also the effects of magnetic frustration, when the magnets just can't line up properly.
Precisely. And that leads us towards this really elusive state called a quantum spin liquid.
Okay, so non-Fermi liquids, quantum critical points, frustration, quantum spin liquids. Quite the list.
It is. And the papers look at specific materials where we see hints of these things. C793, YBMJ04, CePdAl, and SR3Cuta209.
Gotcha. So the mission for this deep dive is to unpack what these studies tell us about these exotic states, why researchers are so intensely focused on them.
And maybe what they teach us about how matter works at a really fundamental level.
Okay, let's jump in. Before hitting the specific materials, maybe we should cover those core concepts you mentioned. First up, non-Fermi-liquid behavior, NFL.
Okay, yeah. So for decades, right, our main way of understanding electrons in metals, especially at low temperatures, has been Fermi-liquid theory.
The standard model for metals, basically.
Exactly. And it's incredibly successful. It treats electrons almost like particles, maybe slightly heavier or interacting a bit, but still quite predictable. But NFL behavior, that's when that standard model just stops working. Breaks down.
Breaks down how?
The electrons, their interactions become so strong, so collective, that you can't really think of them as those simple particles anymore. The old rules just don't apply.
And how do you actually see this? What are the, experimental fingerprints?
You see it in how things change with temperature, really low temperature. Take specific heat, C, how much energy you need to warm it up.
Right.
Normally, C divided by T, CT, it levels off to a constant value as you approach absolute zero. In an NFL system, it might keep going up, often like the logarithm of temperature minus log T.
So it diverges instead of settling down.
Exactly. Or look at resistivity, how hard it is for current to flow. A normal Fermi liquid, it goes like T squared at low T.
The standard behavior.
Right. But an NFL might follow, say, T to the power of N, where N is maybe 1.5 or 1 or something other than 2. That tells you the electron scattering is fundamentally different.
And magnetic susceptibility, how it responds to a magnetic field.
That too. Instead of just becoming constant, it might show weird power laws, like 1 minus T to some fractional power.
Yeah.
These specific dependencies, the logs, the funny power, they're like signposts, telling you you're in NFL territory.
Okay, so seeing these is a big red flag. Something unusual is going on with the electrons. The sources mention different theories for why this happens.
Yeah, because it's not always the same reason. Sometimes it's related to disorder in the material, like the Kondo disorder model. Other times it's about intense fluctuations, spins fighting wildly, or other collective wobbles. Theories like SCR, Hertz-Millis. They focus on those fluctuations.
So the microscopic cause can vary.
It really depends on the material.
Got it. Now you said NFL behavior often pops up near a quantum critical point.
Yeah.
QCP. That sounds pretty fundamental.
Oh, it is. Hugely important. So you know how materials change phase, like ice melting into water as you raise the temperature?
Sure.
Okay, now imagine pushing that transition temperature, maybe from magnetic to non-magnetic all the way down to absolute zero. 0 Kelvin.
The coldest possible temperature.
Exactly. A QCP is a phase transition at absolute zero. But here's the twist. You don't tune it with temperature, you tune it with something else. Pressure, magnetic field, maybe changing the chemistry slightly.
So you squeeze the material or put it in a strong magnet, and you can push it right to this quantum tipping point at 0 Kelvin.
That's the idea. And the really wild part is the quantum fluctuations associated with that point, they don't just exist at absolute zero. Their influence stretches up to higher temperatures.
Ah, okay.
These quantum critical fluctuations can dominate the material's behavior over a whole region of its phase diagram. And they are very often the driving force behind the NFL behavior we just talked about. The QCP is like the engine making the NFL happen.
Okay, that connects those two nicely.
Yeah.
What about the third concept? Geometric frustration.
Right, frustration. This usually comes up when we talk about magnetism, especially in materials with atoms that have their own little magnetic moments like rare earth elements, cerium, ytterbium, things like that.
Yeah.
Frustration happens when the way these magnetic atoms are arranged physically, their geometry on the crystal lattice, makes it literally impossible for all the magnetic forces between them to be satisfied at the same time.
Like your example of magnets on a triangle, trying to point opposite to their neighbors.
Exactly like that. You just can't make everyone happy. Some interactions will always be, well, frustrated, unsatisfied.
And that prevents them from just locking into a simple pattern, like alternating up, down.
Precisely. Even as you cool it right down, the frustration prevents that simple low-energy ordered state from forming easily. The spins might keep fluctuating, or form complex patterns, or stay disordered.
So frustration keeps things interesting, magnetically speaking, even at low temperatures.
Very interesting. It can lead to really unusual ground states, and it's thought to be a key ingredient for stabilizing some of the most exotic things we're hunting for, including quantum spin liquids.
There it is, the connection. Okay, great. So we have NFL behavior electrons acting weirdly. QCPs, zero temperature transition points driving that weirdness. And geometric frustration arrangements that stop magnets from ordering, simply potentially enabling even weirder things like spin liquids. With that groundwork, let's get into the materials.
Sounds good. First up, CePdAl. Cerium, palladium, aluminum.
Which the sources call a frustrated Kondo lattice. Okay, so Kondo affect local magnetic moments talking to conduction electrons plus frustration.
That's the mix. Now, at normal pressure, CePdAl actually does order magnetically, antiferromagnetically, below about 2.7 Kelvin.
Okay.
But the frustration is already showing. The sources point out that even in this ordered state, 1 out of the 3 cerium magnetic moments in the crystal unit cell, it doesn't join the ordered pattern. It stays fluctuating, dynamic.
So it's partially ordered, partially fluctuated right from the start.
Exactly. It's inherently frustrated. Now, the studies looked at what happens when you apply pressure, hydrostatic pressure.
It messes with the order.
It does. It suppresses that magnetic ordering temperature, pushes it down.
Towards a QCP.
Bingo. The ordering temperature goes down continuously and seems to vanish right around a critical pressure, PSE, of about 0.9 gigapascals. That's the quantum critical point.
How did they actually watch this happen? Especially the magnetism under pressure.
A really powerful technique here is muon spin relaxation, or LSSR.
Muons, like the subatomic particles.
Yep. You shoot polarized muons into your sample, they stop, and their internal spin acts like a tiny compass needle. It precesses or relaxes depending on the local magnetic fields it feels from the material's electrons and atoms.
So it's a tiny spy inside the material reporting on the magnetism.
That's a great way to put it. It's incredibly sensitive to magnetism, ordered or fluctuating, at the microscopic level.
Cool. So what did the LSR spies report back from CePdAl under pressure?
Okay, several key things. First, they confirmed the ordering temperature gets smoothly suppressed right to 0 at that QCP, 0.92 GPa. It followed a specific mathematical form, a power law, which is strong evidence for a continuous quantum phase transition.
Okay, confirming the QCP exists. What about the state around that point? Above the ordering temperature or beyond the critical pressure?
This is where it gets really interesting. In that region, the paramagnetic region, they saw the muon signal change its character below a certain temperature they called T-star.
Changed how?
Instead of a simple exponential decay, which you might expect, it became stretched exponential.
Stretched exponential. Okay, that sounds technical. What does it mean physically?
It's often a sign of complexity. It's seen in systems with, say, a distribution of relaxation rates or glassy dynamics or disordered fluctuating moments. In this context, for CePdAl, the researchers interpret it as a signature of spin-liquid type correlations.
Spin-liquid-like, so not ordered, not frozen randomly like a glass, but dynamically correlated disorder.
Something like that. The spins are moving, fluctuating, but not independently. There's some collective dance going on, just not a simple ordered one.
And this temperature T-star where it kicked in.
This was crucial. They found that this T-star, identified from the muon measurements, lined up really well with the temperature scale found earlier from heat capacity measurements.
Heat capacity, what did that show?
It showed an accumulation of magnetic entropy above the ordering transition. Basically, because of the frustration, the spins couldn't get rid of all their disorder, their entropy, by ordering at Tn. Some entropy remained at higher temperatures.
Ah, so the muons are seeing dynamical correlations appear right where the thermodynamics says there's excess magnetic disorder due to frustration.
Exactly. It provides microscopic evidence connecting the frustration, the fluctuating moments, and the spin liquid-like behavior. And importantly, this happens not just at the QCP, but in a broad region around it.
So the frustration is really shaping the physics near the quantum critical point, maybe even stabilizing this odd state.
That's strongly suggested. They also looked at the rate of the muon relaxation, divided by temperature, lot T. This quantity showed a really strong upturn, a divergence as you cooled down towards zero, especially right at and beyond the QCP.
Divergence usually means critical behavior.
Classic signature of quantum critical behavior. It reflects the critical slowing down of the spin fluctuations as the system approaches that zero temperature instability.
Did they do other muon tricks?
Yes. They applied a magnetic field parallel to the muon's initial spin direction. It's called longitudinal field ESR. This helps distinguish static magnetic fields, like in a spin glass, from dynamic fluctuations.
That's all.
A static field would just add to the external field, maybe decoupling the muon. But if the internal fields are fluctuating rapidly, the external field has less effect on their relaxation.
And in CePdAl?
The relaxation rate still diverged strongly as the applied field went towards zero, following a power law. And using something called time field scaling analysis, they showed the dynamics were cooperative and dynamic. Not static disorder, not simple spin glass freezing, collective fluctuations.
Wow. Okay, so let's sum up CePdAl. You have frustration causing some moments to fluctuate even when it orders. You apply pressure, tune it to a QCP. And around that QCP, SSR provides strong evidence for a wide regime of quantum critical behavior dominated by dynamic cooperative spin fluctuations that look like spin liquid correlations.
Frustration seems absolutely central.
That's the picture painted by these sources, yes. A beautiful interplay of frustration and quantum criticality.
Okay, let's switch gears to the next material. Cef7-9I3. Cerium nickel 3, another cerium compound described as a heavy fermion.
Right. Heavy fermions, remember, are these materials often with cerium or ytterbium where the localized electron magnetic moments interact really strongly with the conduction electrons, the Kondo effect.
Making the conduction electrons seem much heavier. Exactly, hence the name. Now, C7-9I3 has a specific hexagonal crystal structure, and it actually has two magnetic transitions at ambient pressure.
Two.
Okay, one at 1.9 K, another lower down at 0.7 K. And the structure itself is interesting. The sources point out that some of the cerium atoms form arrangements, these sort of hexahedra along one crystal axis that look geometrically frustrated. Plus, some cerium atoms are quite close together, which also suggests frustration might be at play.
So frustration possibly lurking here too, but in a heavy fermion system with multiple ordered phases, what does pressure do to this one?
Pressure is key again. It suppresses both ordering temperatures. The higher one, Tn1 at 1.9 K, gets pushed down and vanishes at a critical pressure, PC, of about 0.39 GPa.
Another pressure-induced QCP.
Seems so. And the fact that pressure has such a strong effect tells you there's a delicate balance, a competition, between the Kondo effect trying to screen the moments and the RKKY interaction trying to make them order, even at zero pressure.
And near this 0.39 GPa point, do we see the NFL signatures again?
Oh, yes. Right around PC, they report seeing that characteristic CT varying as minus log T, and the magnetic susceptibility doing a power law thing, chi proportional to 1 minus T to the minus 0.5. Classic NFL behavior near the QCP.
Can we zoom in on the measurements under pressure? What did the specific heat CT show as pressure increased?
Well, at zero pressure, you see two bumps in CT for the two transitions. As you add pressure, those bumps move down and get smaller. Right near the QCP, say at 0.36 GPa, you get a broad hump instead.
Okay.
Now, the sources note something interesting. While it shows that minus log T divergence characteristic of NFL at slightly higher T, right down at the lowest temperatures, it seems to level off, or at least bend away from the log divergence.
So maybe crossing over into a Fermi-liquid state right at the bottom, even near the QCP?
That's one interpretation offered, yes. But
Yeah.
then slightly above the critical pressure at 0.43 GPa, things get even more nuanced. At the very lowest temperatures, CT does look pretty consistent with a Fermi-liquid.
Okay, so Fermi-liquid above PC.
But there's a subtle, shallow bump around 0.4 Kelvin that, well, it shouldn't really be there in a simple Fermi-liquid picture.
A lingering effect.
Possibly. The sources suggest maybe those quantum critical spin fluctuations, even though you're supposedly in the Fermi-liquid phase, are still strong enough nearby to mess with the electronic density of states a bit, causing that little feature, the QCP casting a shadow, if you like.
Fascinating. So the lines can be blurry. What about the magnetic susceptibility at that same pressure, 0.43 GPa? Did it look like a Fermi-liquid?
This is where it gets really curious. No, at the same pressure and temperature range where CT looked like a Fermi-liquid, the magnetic susceptibility kept increasing down to the lowest measured temperature, 0.09 K. It still showed clear NFL character.
Whoa. So specific heat says Fermi-liquid, but susceptibility says non-Fermi-liquid at the same time.
Exactly. It really highlights how complex these quantum critical states can be. Different properties can reflect different aspects of the underlying physics. It's not always a simple, uniform picture.
Definitely not simple.
Yeah.
What did electrical resistivity tell them?
Resistivity also tracked the changes. Below the QCP, features in the resistivity helped map out the magnetic transitions and even suggested the type of magnetic structure might change with pressure, maybe a spin density wave changing its orientation.
Okay.
They also saw resistivity was different depending on the direction current flowed through the crystal anisotropy.
And that anisotropy means?
The interpretation was that it signals remaining spin fluctuations preferentially oriented along certain crystal directions, even inside the ordered phase. As pressure increased further towards 0.7 GPa, this anisotropy disappeared, suggesting those fluctuations were finally quenched.
And at even higher pressures?
Above about 0.66 GPa, it settles into a clear Fermi-liquid state. Resistivity shows that nice t-squared dependence. They also look at the ratio between the resistivity t-squared coefficient and the specific heat coefficient, the Katawaki-Woods ratio. It was a bit large, but not uncommon for heavy fermions.
So pressure takes C7I3 on a journey. Multiple orders. Then a complex QCP and FL region, perhaps influenced by frustration, finally into a Fermi-liquid state. Did magnetic field do anything interesting?
Oh, yeah. Very anisotropic response again. The field along one direction, the magnetic order was tough, but field along the C-axis, the main order vanished at quite low fields.
A field-induced transition.
Looks like it. And above that field, a new magnetic phase appeared at higher fields, above 0.7 Tesla. Interestingly, in the intermediate field range, between the suppression of the old order and the start of the new one, neutron diffraction found evidence for short-range magnetic order below 1 Kelvin.
Short range, so not fully ordered, but not random either.
Right. Correlations over short distances, but no long-range pattern. And the sources explicitly link this, and the large spin fluctuations seen in that region, back to that potential geometric frustration involving the CI and CThen sites.
So the frustration might be preventing full order in that specific field window.
That's the suggestion. It keeps the spins fluctuating and only allows short-range correlations. The high field phase itself was found to have a complex structure, with the magnetic pattern repeating over a larger distance in the plane.
So C7Na3, much like CePdAl, really showcases this intricate dance between frustration, the Kondo effect, quantum criticality, tuned by pressure and field, leading to NFL behavior, crossovers, and these intermediate phases with significant fluctuations.
Exactly. Frustration seems to be a recurring theme, disrupting simple magnetic order and enabling these more complex behaviors.
Okay, let's shift focus now directly onto quantum spin liquids, QSLs. We've hinted at them, this exotic state potentially born from frustration.
QSLs, yeah, they are really one of the holy grails in condensed matter physics right now. Conceptually, they're states where even if you cool them down to absolute zero, the spins never settle down. They don't freeze into a standard magnetic pattern, ferromagnet, antiferromagnet, nothing like that.
They stay.
Yeah.
Liquid, even at 0 Kelvin.
That's the analogy. They remain in this highly entangled, dynamic, fluctuating state, driven by strong quantum effects and usually frustration.
Entangled and dynamic at 0 temperature. How is that possible?
It comes down to the quantum mechanics being dominant. A key idea mentioned in the sources is that excitations in a QSL aren't simple spin flips or waves like in normal magnets.
Yeah.
They can be these weird fractionalized things like spin-uns, which might carry, say, half the spin of an electron.
Fractional excitations. Okay, that is weird. So finding materials that actually do this must be hard.
Extremely hard. That's a major point in the sources. Theory predicts QSLs might exist on certain geometrically frustrated lattices, like triangles or Kagome patterns, but real materials, they're never perfect.
What kind of imperfections get in the way?
All sorts. Maybe the lattice isn't perfectly symmetric, so interactions are stronger in one direction, anisotropy.
Yeah.
Maybe different types of atoms get mixed up on the magnetic sites. Maybe layers of magnetic atoms interact too strongly with each other, spoiling the ideal 2D picture.
And these problems can kind of mask or destroy the QSL state.
Right. They can nudge the system towards conventional ordering or introduce randomness that mimics some QSL features but isn't the real deal. So the hunt is on for materials that are as structurally clean and close to the ideal theoretical models as possible.
The sources highlight two candidates considered really promising, specifically for QSLs on a triangular lattice with spin 12 moments.
Yes, the spin 12 triangular antiferromagnet is a classic theoretical battleground. You have maximum frustration from the geometry and maximum quantum fluctuations because it's spin 12, it's prime territory.
Okay, let's take the first one, YBM GAAO4, ytterbium magnesium gallium oxide.
Right. This one generated a lot of excitement when it came out because structurally it seems to tick a lot of the ideal boxes according to the sources. Well, first, it has really high crystal symmetry, R3-more, which means that triangular layers of ytterbium ions are very isotropic. The magnetic interaction should be the same in all directions within the layer. That's a big plus.
Okay, avoids anisotropy. What else?
There's very little mixing between the magnetic ytterbium YB3 plus ions and the non-magnetic magnesium gallium ions on the lattice sites. They're chemically different enough to stay put.
Good. Avoids site disorder.
Also, the magnetic YB layers are separated by thick, non-magnetic double layers, making it effectively very two-dimensional. Interlayer interactions should be weak.
Crucial for comparing with 2D theories.
And structurally, there are inversion centers located between the YB ions. This symmetry forbids a certain type of magnetic interaction called the Dzaleshinsky-Moria, or DM interaction. DM interactions can often favor weak magnetic ordering, so ruling them out is good for QSL prospects.
Wow. So structurally, it looks about as perfect a spin 12 triangular lattice as you could hope for.
That's the argument made in the sources, yes.
Yeah.
And the experiments. They are pretty compelling. First off, despite clear signs of strong antiferromagnetic interactions, the Weiss temperature is around -4 Kelvin. There's absolutely no sign of magnetic freezing or ordering down to incredibly low temperatures, 60 millikelvin.
No ordering, despite the interactions trying to make it happen.
Classic
sign of frustration doing its job.
Exactly. Then they looked at the heat capacity at low temperatures. It follows a power law. C proportional to T to the power of about 0.7.
A power law instead of, say, an exponential decay.
Right. Exponential decay would suggest an energy gap. You need a minimum energy to create an excitation. A power law suggests gapless excitations. You can create them with arbitrarily small energy. The estimated gap is tiny, like less than 1% of the magnetic interaction strength.
Gapless. Is that backed up by anything else?
Yes, the magnetic susceptibility also stays finite, non-zero, as you cool towards absolute zero. That's also consistent with a gapless state. And maybe the most convincing piece, they carefully measured the entropy.
The magnetic disorder.
Right. By comparing to a non-magnetic version, they could isolate the spin entropy. And they found that as they cooled down, the residual spin entropy went essentially to zero.
Why is zero residual entropy important here?
It means the system seems to have found its true ground state at the lowest temperatures measured. And that ground state is highly disordered, consistent with a QSL, but without any leftover entropy that would need to be released by some hidden ordering transition at even lower temperatures. It suggests the disordered QSL state is the stable ground state.
That sounds pretty definitive. Did they see anything in magnetic fields?
One more curious thing, they saw a strange plateau in the magnetic susceptibility when they applied a field, between about 1.6 and 2.8 Tesla at half a Kelvin. Just a flat region where you wouldn't expect one for a simple paramagnet. It hints maybe the field induces some other unconventional quantum spin state.
Okay, so YBMJEO4. Near perfect structure, no ordering despite strong interactions, gapless excitation seen in heat capacity and susceptibility, zero residual entropy. Points strongly towards a gapless QSL state on the triangular lattice.
That's the conclusion presented in these studies, yes. It's a landmark candidate material, even if some debates continue about the precise nature of the disorder.
Now, the other triangular candidate mentioned, SR3Q209, SCTO.
Yes, SCTO. Strontium copper tantalum oxide, another promising spin-12 system. It's part of a family called triple perovskites. The structure is clever. The copper C2+ ions, which carry the spin-12 moments, and the non-magnetic tantalum Ti5+ ions order themselves nicely.
How does that create the triangular lattice?
It results in layers where the copper ions effectively form an edge-shared triangular lattice. So different structure overall, but the magnetic layer has that key geometry.
And is it strongly frustrated?
Very. The sources quote, a frustration parameter F the ratio of the interaction strength to any potential ordering temperature as being greater than 76. That's huge. Indicates very strong frustration.
Okay. And the evidence for a QSL? Does it also avoid ordering?
It does. Again, no sign of magnetic long-range order or spin freezing detected down to 0.1 Kelvin, using both specific heat and, importantly, LSR again.
Muons again, so persistent fluctuations.
We'll get to that. First, the specific heat. Below about 1.2 Kelvin, the magnetic part, CeLe, again, follows a power law. C proportional to T to the power of eta, and here they find eta is very close to 23.
2/3. Is that number special?
Very special, potentially. The sources highlight that an exponent of 23 for the specific heat is exactly what's predicted by some theories for a QSL state that hosts a spin-ion Fermi surface on the triangular lattice.
Whoa! A Fermi surface,
Yeah.
but made of spinions, those fractional things.
Exactly. The idea is that these fractional spin-ion excitations might behave collectively somewhat like electrons at a Fermi surface, leading to this specific T23 dependence in the heat capacity. Seeing that exponent is incredibly suggestive.
That's a really specific theoretical prediction seemingly showing up in experiment. What did the muon say about CePdAl?
The zero-field METASAR was striking. The relaxation rate became completely temperature-independent below 1.2 Kelvin.
It just flattened out.
Flattened out. That's considered a hallmark of persistent spin dynamics down to the lowest temperatures, exactly what you'd expect in a QSL, where the spins never freeze. They keep fluctuating at a constant rate. Longitudinal field METAS also confirmed these were strong dynamic correlations, not static freezing.
Any other evidence?
They also mentioned thermal conductivity measurements, how well it conducts heat. At low temperatures, the thermal conductivity didn't go to zero. It extrapolated to a finite value at zero temperature.
And that means?
It suggests there are gapless excitations present that can carry heat even at T0. Again, consistent with a gapless QSL state, possibly with that spin-in Fermi surface providing mobile carriers.
So CePdAl looks like another really strong case. No order, power law specific heat with that suggestive 23 exponent hinting at a spin-in Fermi surface, persistent dynamics in ESR, finite thermal conductivity. Multiple lines of evidence pointing to a gapless QSL.
Yes. And just like with YBM GA04, the sources contrast this QSL finding with the simple expectation for a basic triangular lattice Heisenberg model, just nearest neighbors, which should probably order. It again implies that the details of the interactions in CePdAl, maybe longer-range couplings or other subtle effects, are crucial for tipping the balance towards this exotic QSL state.
It really hammers home that point. The specific material context, the precise interactions, they matter immensely. Same lattice geometry doesn't always mean the same outcome.
Absolutely. You need the right ingredients, frustration, strong quantum fluctuations, maybe specific interaction paths to cook up these truly non-trivial quantum states.
Wow, okay, what a tour. We started with these general ideas, non-Fermi liquids, where electrons forget the rules, quantum critical points as the knobs tuning them.
Then saw how geometric frustration is more than just a concept. It actively shapes the behavior in real materials like CePdAl and C7Ni3, messing with magnetic order, contributing to fluctuations near QCPs.
And finally, how that frustration, especially in structurally clean systems like YBM GA4 and CePdAl, might be the key to unlocking these incredibly exotic quantum spin liquid states with weird properties like gapless fractional excitations, maybe even a spin-ion Fermi surface.
Yeah, these studies really are pushing right at the frontiers of condensed matter physics. They're challenging our old frameworks and revealing just how rich and strange the quantum world can be when electrons and spins interact strongly under the right conditions.
It's definitely not just textbook physics anymore. It makes you wonder, doesn't it? If tuning pressure or tweaking the geometry or just the specific mix of interactions in a material can lead to states like spin liquids, where everything we thought we knew about magnetic order just dissolves.
What other completely bizarre, totally unexpected quantum states of matter might still be hiding out there, waiting for us to find the right material, the right conditions, the right combination of frustration and quantum mechanics?
A very provocative thought to end on.